today. All right. The last thing I need is pen. Tis a large blank space, but it's too big. So we're not going to fill that. All right, here we go. This is a re-warm up of Le Chatelier's principle. All right, to get you guys back into the groove a bit. Synthesis of hydrogen iodide. So I have this equation right here. H2 plus I2 is equilibrium with 2HI. Delta H is positive 0.51, which means I have to write heat over here as a reactant. So I write plus heat. I write plus heat as a reactant. So let's talk about stresses that we could do. One stress would be if I would increase pressure. If I would increase pressure, how would this shift? Which way?
The least moles of gas.
Okay, so it's a which way would it shift?
Wait, you increase pressure on which side? The left.
I'm increasing pressure on the whole equation.
Oh. Nowhere?
Why?
Because you're increasing pressure on both sides unless you're increasing pressure.
Nope. Which way would this shift? Would it shift left?
Right.
Why?
Because the other things that's a...
No.
Because there's less moles of gas on right hand side, so pressure is reduced.
No, there's not.
For real? The same line.
They're the same.
They're the same.
So which way will it shift?
No.
None. There will be no shift. Yeah, but you didn't explain it why. Right.
What?
You just said because.
He said no instead of why.
Well, your why wasn't right. None. Because I have the same number of moles of gas on each side.
I was way overthinking.
I know. That's why we're warming our brains back up here. What would happen if I increased temperature? Which way would it shift?
Exothermic FE. Wait, so it would
Will it
be...
shift right? Will it shift right because you're adding more reactors?
It will shift right. Because I rewrote heat as a reactant, yes. Reason is, it's endothermic. It's endothermic. This reaction requires heat. So if I'm adding more heat, it's going to push it farther to the right. What would happen if I increase the concentration of H2? Which way would it shift?
Right again.
Why?
Because H2 is a reactant, and so adding more reactants shifts the opposite direction.
More reactants. So Q is going to do what? If we're going to be super descriptive here. Q will go up or down. If I add reactants, my Q is going to be decreased, right? If I'm adding more reactants, it's products over reactants, yes? Yes? So shifts right to bring Q back equal to K. And then the last one, if I increase concentration of HI, which way will it shift? Left. Because the opposite, more products. So Q increases, so it has to shift to the left. It has to shift to the left. So that's a little review of what we were talking about Friday. I will. Look, I just got like 12 texts. I'm going to catch up on those while you guys are.
This is more boost, so Q increases, right?
Q is...
All products with Q can increase.
Are we saying to balance Q plus K?
Yes.
Pressure time.
All right, what about solids?
Oh.
What about solids? So all sodium, potassium, ammonium, and nitrate salts are what in water? Completely, pretty much. They're basically completely soluble in water. But some other salts are considered to be insoluble. In reality, even insoluble salts dissolve a little. They dissolve even a little bit. And equilibria are set up in solution. For example, it's possible to set up an equilibrium where a saturated solution, one where the maximum amount of solute has been dissolved, of silver chloride is in contact with undissolved solid silver chloride. So, check this out. Here's my solid silver chloride. Yes, in equilibrium with its ions. In equilibrium with its ions. Since pure solids are omitted, right? Yes? From the K expressions, the KSP are to be rewritten how?
I can't do it over nothing.
Yes, I can. Why can't I?
Just be over 1 would.
It'd be over 1 or nothing. Over nothing means over 1, right? So it'd be concentration of
Oh.
Zero.
Ag plus, it's not 0, times the concentration of Cl minus. So the nice thing about KSP is that it's not over nothing, it's over what? 1. So these are a little bit easier to solve. Flip it. KSP is defined as the product, which makes sense, of the equilibrium concentrations of the constituent ions raised to their stoichiometric coefficients. Raised to their stoichiometric coefficients, and is called the solubility product. And that's the SP part of it. It's called the solubility product. The smaller the value of KSP, the smaller the number of ions that have gone into solution. Therefore, the less soluble. So, big KSP, it's soluble. Small KSP, it's not very soluble. The compound is in water. The concentration of the ions that have gone into solution is usually expressed in terms of molar solubility. Molar solubility. For example, the number of moles of a solute in 1 liter of a saturated solution. However, solubility may be expressed as the number of grams of a solute in 1 liter of saturated solution. So, if you have grams, what are you going to have to do? Convert. So sometimes they'll give you grams per liter instead of moles per liter, so you have to do a little bit of stoich with these. So, calculating KSP from molar solubility. Here we go. At a certain temperature, the molar solubility of the salt M plus 2, X negative 2, is found to be 4.15 times 10 negative 6 molar. Calculate the KSP for the salt. So we know that KSP is going to equal concentration of M plus 2 times the concentration of X minus 2. Agreed? Yes? So, I'm going to sub in what I know. KSP is going to equal 4.15. They're giving me the molarity. Times 10 negative 6 times 4.15 times 10 to the negative 6. It's going to be the same for both ions, agreed?
Is there ever going to be a situation where it's not?
How do I know it's the same?
Because it's XM, so they should both be the same amount. Because it's like more.
Oh, there's only 1 mole per, like, there's only 1 mole of M per 1 mole of NF.
Yes. Also, the charges are the same as well.
So if X was like X2.
Then it had to be squared, correct.
Okay.
You got it. So it's just basically just this squared. So KSP, put that on your calculator, you get 1.72 times 10 to the negative 11th. That's pretty small.
That's not very soluble.
Not very soluble at all. Not very soluble at all. Calculating KSP from solubility expressed in grams per liter. At a certain temperature, the solubility of calcium sulfate is found to be 0.66 grams per liter. Calculate the KSP for the calcium sulfate. First thing I would do would be convert grams to liters to molar.
Should you always put it from the...
Yes. So 0.66 grams over 1 liter and this is grams of CaSO4.
We need to bring out the molar mass.
I'll just tell you, it's 136.14 grams of CaSO4 for every 1 mole of CaSO4. So that gives me 0.00485 molar. Now I can put that into my KSP expression.
0, 0 is at 45.
Yep, KSP is going to equal concentration of Ca what?
Oh, see.
Plus 2 times the concentration of SO4, which is a minus 2. So KSP is going to equal essentially 0.00485 what? Squared.
Is it okay for us to write it as?
Sure. I know what that means. We'll know what that means in the AP test. So KSP ends up being 2.35 times 10 to the negative fifth.
So, better than the previous one, so not very soluble.
So not very soluble. Better than one before. And we're going to talk about, I think on the next page I talk about what's considered soluble and what's not. So I'm going to give you an actual number. Working backwards. So on this one, I want to solve for the molar solubility of Ag2SO4. So on this one, first thing I'm going to do is I'm going to write an equation. So I have Ag2SO4. That's a solid. Agreed? Yes? Is in equilibrium with what?
Ag plus 1 and SO4.
Be careful.
Like a 2 Ag.
2 Ag plus 1. Agreed? Yes? Yes? You okay where that number came from? Plus SO4 2 minus. So that's my reaction. Now I need to ice it. Got to ice it. What is my initial concentration of the solid? Does it matter? Do solids go in an ice table? Solids don't go in an ice table. They're not part of equilibrium. Agreed? Yes? Where's my initial concentration of these ions? It's a decomposition reaction. So it starts out as what? 0, right? If it's decomposition, right? Do I start with any products? No. My change, still not part of it. What's my change going to be for Ag? Not 1/2. First of all, plus or minus. It's going to be plus or minus. I'm making products, so it has to be plus 2x. Plus 2x because coefficient of 2. And the other one's just going to be plus what? Plus x. So E, not part of it, is going to be 2x and x. So sometimes you'll see an ice table called a rice table.
Either way.
So, because the R is just a reaction. So I just want to show you that. Kind of fun. So a rice table is just an ice table with a reaction. I know, mind blown. So KSP is equal to Ag plus 1 to the power of 2 times SO4 2 minus.
Why don't you put the 1.4 in case?
I should have. I will in a second. I'm just working it out. So KSP is equal to 2x squared times x. So KSP equals what?
Two x to the
4x cubed,
Oh, it's multiplication.
right?
2 squared x.
Oh, shoot, I'm still writing stuff down. That was what we were on.
4x cubed? Are you okay with that?
Yeah, that's good.
KSP equals 4x cubed. Now I sub in my KSP. I just want to write it 5 times, Jack.
Divide by 4, then cube root.
Yes. So I have 1.41 times 10 to the negative fifth equals 4x cubed. So do that in your calculator and solve for your molar solubility. Let When you started saying to the fifth, I was getting nervous.
No, but I can't. You have no room to talk after you said divide by ln.
So divide by 4. Wow, she brought that back.
I think that's it.
It's n3.
Or power to the 1/3. So I'm 22 days into my no Mountain Dew and desserts journey. But since I've started doing this, I've hit my water goal every single day. I know. Pop makes you not thirsty, I've determined. So I've had 23 days in a row of hitting my water goal. So I have no idea how I'm going to measure that in Disney World. I probably won't, in all honesty. I'm probably not going to take this with me to Disney. Just because you have to have a flat surface to set it on. I'm going to have a water bottle in my backpack, right?
Disney.
Also, when that hits 50, I'm going to Disney. So that's also like almost becoming a countdown for me.
You like that?
4 weeks from today. But I'll see you that day because I'm taking a half day. I have an appointment that afternoon before I fly. So,
Is that the last week of February?
yes, it is. What'd you guys get?
0.01.
X equals 0.0152 molar. Boom. So these are not hard. Full disclosure. First year I taught AP, I did not know about KSPs. Yeah. Luckily it wasn't on the test that year. A tip and a word of warning about QSP, KSP values. First of all, what would a QSP be? That'd just be KSP at a beginning, right? A direct comparison of QSP to determine the relative solubility of a sparingly soluble salt should only be made when two salts involved have the same ratio of cations to anions. We just showed that, right? If the ratio is not the same, if it's not a 1-to-1, what do I have to do? We just did it. If it's not a 1-to-1, I have to ice it, right? So when they have the same X expression, for example, AgCl and BaSO4, those would work because their ratio of ions are both a 1-to-1. And their Q and K expressions are both K equals X squared. I can, so sorry. Agreed? The larger K will result in a larger square root of K, hence the larger X value, hence the greater solubility. But this can't be done with salts that have different ratios. So if you had KSP for FeOH2 is 8.0 times 10 to the -16th, and the KSP for AgBr is 5 times 10 to the -13th, you would have no way to know which one's more soluble. Does that make sense by looking at it? Yes? Because you think the larger one shows that AgBr is more soluble, but if you solve for X, you would actually find this, that they're not. So be careful, is what I'm saying. If they're both 1-to-1 and you have two KSPs, you can directly compare. If not, you can't. Okay. AP may ask you to infer. KSP values rather than simply recall solubilities. For example, it may not be sufficient or enough to simply know that AgCl is insoluble, but rather you may be expected to say something like the KSP value is 1.8 times -10th and is very what? Small. So they would give you a KSP in this. You don't have to memorize it. They'd probably give you a chart of KSPs and say, why is AgCl insoluble? Well, you would need to use the evidence they gave you. This suggests that very few ions are in solution and that the salt is essentially insoluble. But AP, here's the number, is basically cool. If KSP is greater than 1, it's soluble.
That's so nice.
I know. I just wanted to get to that so you guys can see that.
A chart with different KSP values, and like there's not like one greater than 1 on there. Like, how do you just determine the relative like solubility based off the table?
Correct. Compared to each other. Okay. All right. So, to review, delta H is what? What did that mean? That's not in this chapter.
Oh.
So no, that's H weight.
Yes, Jack. Enthalpy. I think we've talked about delta S very briefly. Maybe not though. Delta S is entropy. So we're not going to talk a lot about this a lot yet, but I just wanted to hit it for a quick second. Entropy is disorder. We'll talk about that more in Unit 9. But I just wanted to talk about this little paragraph before we move on. The separation of solute particles from one another, if you break these up, is endothermic, right? If you're breaking it up, you have to put energy in. Agreed? The separation of solvent particles from one another, so breaking the bonds, would also be endothermic. The interaction between the solid particles and the solvent, for example, ions becoming hydrated when ionic substance dissolves, is exothermic. The other thing I wanted you to consider is when you dissolve something, entropy increases. Think about that. Salts have what form? The crystal lattice. When I dissolve that, there's ions everywhere, right? So disorder increases. So dissolving something increases entropy. That was just a little thing I wanted to hit. Flip it. The common ion effect. This is big. This is going to be our POGL tomorrow. Yes. If a solution contains two dissolved substances that share a common ion, then the solubility of a salt becomes more complex to determine. For example, it's relatively easy to perform calculations relating to the solubility of a saturated solution of silver chloride in water, since all the silver ions and all the chloride ions came from the solid. Make sense? The silver chloride. If, however, we wish to study a solution that contains both silver chloride ions and silver nitrate, oh snap, now I've got silver coming from two different places.
Kind of isolate the silver somehow.
Then a more complicated situation arises. So two sources of silver, the silver chloride and the silver nitrate. You have to ice whenever there's a common ion. So here we go. We're going to do a couple examples of this. Number one, given the KSP for silver chloride is 1.58 times 10 negative 10th, calculate the molar solubility of silver chloride in A, pure water. So let's do A first. So letter A, my reaction is going to be the same for all of these. AgCl, which is a solid, is in equilibrium with Ag plus Cl minus. So AgCl is not part of this, right? It's a solid, yes? Do I start out with any Ag or Cl from any other source on letter A? Is there any silver or chlorine in water? So my initial is going to be what? 0, 0. Change, not part of it. So this first is going to be plus X. Agreed? E, not part of it. XX. Which means that my KSP equals what? X squared. Not 2x squared, just x squared. So that means that 1.58 times 10 to the negative 10th equals x squared. When you solve for x, you should end up with 1.26 times 10 to the negative 5th molar. So there is no common ion on this one. On B, that changes. So letter B, let's write our equation again. It's going to be the same equation. So my reaction is still AgCl solid is in equilibrium with Ag plus Cl minus. Initial, solid not part of it. What is my initial concentration of Ag? It's 5.5 times 10 to the negative 3rd molar. Where did that come from? That came from, this says that I started out with a silver ion concentration. Chlorine is still what?
X.
0. To start. Change, not part of it. So this is going to be still plus X. Still plus X. Equilibrium, 5.5 times 10 to the negative 3rd plus X and X. So, once again, my KSP is going to equal concentration of Ag plus times concentration of Cl minus, sub in. So I'm going to have 5.5 times 10 to the negative third plus x times x, right? So KSP equals 5.5 times 10 to the negative third x squared plus x. Wait a second. No, you're right, just x. It would just be x, right? 5.5 times 10 to the negative third x plus x. Yes? Plus x squared. There's the x squared. Plus x squared. Sorry. My distribution's a little off this morning.
Oh, that becomes a.
So KSP, right, is 1.58 times 10 to the negative 10th is equal to 5.5 times 10 to the negative third x plus x squared.
There's just quadratic. Is there? Yeah, it's quadratic formula.
So that would be on this one. Yeah, you'd have to do a quadratic formula. But, or graph it. If you graph it, I'm just going to give you the answer. All right? You get 2.87 times 10 to the negative 8th molar. So, what just happened to my molar solubility? Did it go up or down? That makes sense, right? Because if I'm adding in product, which way is it going to shift? Back to the left. Yes? Correct. So your solubility is going to go down. Your solubility is going to go down. So, last one. For C, reaction, AgCl is in equilibrium with Ag plus Cl minus. I, not part of it. On this one, I have a 0.025 molar potassium chloride solution. Do I have any silver to start? On letter C? No. Do I have any chlorine to start?
Yes.
How much? 0.025 molar. And that's coming from this solution, the common ion. Coming from the common ion. C, not part of it. Plus X, E, X, 0.025 plus X. So, we know that 1.8 times 10 to the negative, wait a second, why do I have 1.8? 1.58. 1.58 times 10 to the negative 10th is going to equal X, right?
Yes.
Times 0.025 plus X. So 1.58 times 10 to the negative 10th equals X squared plus 0.025X. Graph it, do quadratic formula, but X ends up being 6.32 times 10 to the negative 9th molar. It's even lower. Well, that makes sense, right? Because this is an even higher concentration than the last one.
Oh, yeah.
Yes?
What if 5.5 10 to the negative third?
You got it. But that's bigger,
The other one
yes?
times 10 to the negative 8.
Negative 8th, negative 9th. So when you think about the common ion effect, it really does make sense. That's just the math behind it. Can I flip the page? What about P? Yeah, I know. We're almost on like the last two of Unit 7. It's a huge unit. It's a huge unit. What about pH? What about pH? When one of the ions in a salt can act as an acid or base, pH can influence solubility. My voice just went weird. Did you guys hear that? pH. Did you guys hear that? No. For example, in the case of iron 3 hydroxide, the following equilibrium can be established. So here we go. FeOH3 solid is in equilibrium with Fe3 plus 3OH minus.
That's a base.
That's a base. Agreed? Addition of an acid to the equilibrium mixture will cause OH minus ions to be removed. Why? Why would an introduction of H plus? Because that's going to make water. Agreed? Yes, HOH is water. Removed in a neutralization reaction. So, as a result, the equilibrium will be shifted which way? If I'm removing product, it's going to be shifted towards the right. Going to be shifted. Beep. Shifted toward the right. Hope that wasn't on the recording, man. Or forward. Does that make sense? Yes, what just happened there? I'm adding in H. It reacts with the OH. It makes water. I'm lowering my products. Shifts to that side. According to Le Chatelier's principle. And the solubility of iron 3 hydroxide is going to do what?
Shifting right.
You tell me. It's shifting to the right. I'm getting more ions.
Increase.
Oh, increase.
Increase.
It's just a ping pong. It's just going back and forth.
It increases. So if it's shifting to the right, I'm getting more ions, more dissolved. Addition of a solubility. Addition of a base to the equilibrium mixture is going to shift it to the left. Because now I'm just adding straight more products. Yes? So the solubility would decrease in that situation. More complicated scenarios arise when the anion of a salt is a strong base. Because a strong base does what?
Right.
No.
Bro.
What do strong acids and strong bases do? Completely dissociate. Right? Yes. We gotta think about these things. It's all related. For example, it is the salt of a weak acid. For example, silver ethanoate that sets up the following equilibrium in solutions. So check this out. Here's my silver ethanoate. That breaks up into silver and CH3COO minus. If we increase H plus on this one, in other words, make it more acidic, the hydrogen ions are going to want to react with the negative. Agreed? So, hello. I could do that. Okay, thanks. All right, so I'm adding in H plus. So the H plus is going to want to react with what? The negative, and that's going to make more what?
The right.
But where did the silver go?
What do you mean the silver? Well, I'm just talking about what this is going to do.
Oh,
Okay, I don't care about the silver. The CH3CO ions are removed from the equilibrium mixture because they reacted, they made something else. Yes? And the reaction is going to be shifted to the right. Going to go to the right according to Le Chatelier's principle, meaning the silver ethanoate is more soluble at low pHs. So, you're just seeing what reacts.
I'm just going to take your word for it.
You're just going to see what reacts. All right. Yes, I think we're going to finish this. The final example involves lead 2 carbonate that sets up the following equilibrium in solution. So here's my equilibrium.
What does that mean?
Lead? Solid?
In the carbonate ions.
Huh?
The I'm looking then.
Where?
Underneath that.
That.
CO3 plus H plus.
Right there. Right there.
Probably. Let's just listen for you. Here we go.
Yeah, looks like a Scorpio symbol.
I'm just trying to figure out if we're going to actually finish this. I think we're going to. I'm trying to figure out what that is supposed to be.
Okay.
And with an arrow.
Guys, I think it's an M.
What? That is Oh, that's my equilibrium.
Oh.
Oh,
Okay.
Okay, that's my equilibrium. Okay, I was getting worried for a second there. So, in an acid, if I add more H+, the H+ is going to react with the CO3 2-, and that would make this. So, the lower, because acids have a low pH, the more CO3 2- are removed from the equilibrium system of lead 2 carbonate in the first equation, causing the equilibrium to be shifted to the right, and therefore increasing the solubility of lead 2 carbonate. So here we go. Consider the dissociation of iron 3 hydroxide. Here it is. In which of the following pHs would you expect iron to be the most soluble? 4.5, 4.6.7, or 11.1. So, if I want it to be more soluble, I want to shift it which way? To the right. So which one of these, high pH or low pH? So first of all, high pH is more basic, yes? If I add in more OH, is that going to shift it to the right?
Yep.
No. That's going to shift it to the, it's going to shift it to the what? I'm going to have to rate these notes PG-13. No, I think it's R now, actually. Shift it to the left, right?
You're adding in more products and so.
I'm adding more products. If I added in more H, it's going to do what with this OH? React, turning that into water, lowering my products, therefore shifting it back to the products. So the answer is 4.5. 4.5. What's the solubility of PbOH2 in a solution pH 9? A solution with pH 9 has a concentration of OH 1 times negative fifth. Okay.
That's a great question.
So here we go. Step 1, let's write our K expression, or just our equation. Pb OH2 is going to be in equilibrium with Pb plus 2 times concentration of OH minus. Huh?
I thought we were writing the equation.
What?
I'm breaking, this is my KSP.
Oh, okay.
I'm writing my K. This is a solid,
Yeah, that makes sense.
right?
What?
I'm not writing the equation, I'm just breaking it up.
Oh, okay. I thought we were writing it.
PB.
Why is there an equilibrium? So, okay, whatever.
Hold on.
I don't care. I don't know that.
Plus OH, and this is going to be what? My OH has to be squared. Yes? Minus 1. So, they gave me 1.2 times 10 to the negative 15th is equal to concentration of Pb plus 2. Sorry, I went straight to the K expression.
Yeah.
We're good though.
Sorry. 1.2 times negative 15th equals Pb times OH negative 1 to the second. So they, on this one, they gave me the 1, right? Yes? So 1.2 times 10 negative 15 is an equilibrium, or equals, X, right? Times 1.5 times 10 to the negative, times 1 times 10 to the negative fifth. That thing should be squared.
And there's no X on that?
Well, the X, this was an X, but they gave it to me.
Oh, okay.
It has this concentration of 1 times 10 to the negative fifth. Solve for X, and X ends up being 1.2 times 10 to the negative fifth. Oh my gosh, we did it.